So we've got our acceptable range. Now I have not yet told you how do we actually choose alpha. I have only given you tests for alpha. Is this alpha good enough? Here are 2 tests or 3 tests, right? Sufficient decrease, Wolfe condition, strong Wolfe condition. Now how do we actually come up with an alpha, right? So let's talk about the simplest algorithm. Simplest algo for finding alpha. Okay. The name of this algorithm is called the backtracking line search. Okay. And in terms of algorithms, it's really simple, like most of the things that we will talk about in this class. Step 1, start with, so if you are in charge of figuring out how to pick alpha, should your starting point be very small alpha or very large alpha? Right. If you are ambitious / impatient, what would you do? Pick a large alpha, right? So start with large alpha. Who knows, maybe you will get lucky sooner, right? Start with a large alpha, okay. Check, let us check the, for example, we can check any of the Wolfe conditions. We could, so let us, for simplicity, let us just say sufficient decrease. You could put in the other one also. So f of x k plus alpha pk, this I want it to be less than the C1 times the linear approximation, right? So check if this is true. Okay. Supposing it is not true, what would you do? Right. So if not true, I need to reduce alpha. So I could do something like alpha new is equal to alpha old multiplied by rho, where rho is some number between 0 and 1. Reduce it a little bit. Sounds quite straightforward, right? If it is true, what do I do? Done, accept it. Quite simple, right? So you can see the why we are using the word backtracking over here. I start with a large value and I keep backtracking until the condition is satisfied. Here we put backtracking for the simple reason that backtracking is n times cheaper than, sorry, here I chose sufficient decrease because sufficient decrease is n times cheaper than curvature condition. But if for some reason curvature is easier for you to evaluate, right, then you could choose that as well. Okay. So I think, let's see, yeah, this is one of the most common techniques by which we can figure out what is the alpha, right? So this is actually your first algorithm of the course in some sense. Given a search direction, start with a large value of alpha, keep backtracking until the condition is satisfied, and then move from xk to xk plus 1. Once you are at xk plus 1, right? You need to repeat it at each. Okay, so if I were to nest it, what would I do? Start with a large alpha, check if this, if true, accept alpha. What does that imply? Xk plus 1 is equal to xk plus alpha pk is set. But is that the end of the problem? No. What is the end of the problem? So now I need to check if grad fk plus 1 is small or 0. If it is true, then victory. If it is false, what do I do? Right, then I need to go back over here, right? So that is the outer loop, you can think of it. The outer loop is to check for gradient, the inner loop is to check for a good value of alpha, right? And that's how you do it. So in subsequent modules we will look at how do we, how good is the convergence, does it converge, things like that. Okay, kya question?
Is it good to choose alpha as a large value, or
Say again?
can we always choose alpha as a big value, or can we have some other, how do we know that whatever value we have there?
So the way we have written this algorithm is a little heuristic, right? So now when I say large alpha, how large an alpha, right? So here the point is that what are we finally using over here? First order linear approximation. If I choose alpha to be very large, 10 to the 6, there's no point of this checking condition, because it's not going to tell me anything. So I need to be, by large I don't mean very very large. So again there is a heuristic flavor over here to tell you what is the value of alpha to be chosen. Okay. So then there are different implementations that people will do. For example, if I normalize the pk to 1 to be a unit vector, many people will start with alpha equal to 1 and then go down. Okay. And here it's like a geometric progression over here, right? So if for example rho is 0.8, right, I reduce alpha at a certain rate. If alpha is 0.1, then within 5 steps I am at 10 to the minus 5, it will get accepted, right? So there's a lot of tuning over here. There is no good, these all things will control the rate of convergence. What you have to be careful of is, in your grid you don't skip the solution. So, there is a lot of research over here in making rho also adaptive iteration to iteration, right? So, and what alpha I choose at one step will not be the alpha I choose at another step. So, technically speaking, some of you should have objected in me writing alpha. Actually, I should write it as alpha k, because for every iteration alpha k may be different. And in fact, as I get closer and closer to the solution, should I expect smaller alphas to work or bigger alphas to work? Smaller alphas to work, right? So you can bake that into your choice of rho also. So a lot of scope for creativity over here. Okay, so that's all I wanted to tell you about line search algorithms. So we looked at, what we looked at was, in the line search algorithms, we looked at, first of all, why do we need to go for inexact line search, right? Because exact line search is extremely expensive. And then we looked at the condition of sufficient decrease, that my function value should be at least below the linear approximation with some relaxation. The second one was called the curvature condition, which looked at the slope. The slope should at least be less than the slope of the linear approximation. This is to prevent very very small values of alpha. And then we did a very obvious fix to prevent overshooting. We put mod on the slope and we got the so-called strong Wolfe condition, right? We may not have even bothered with this regular Wolfe condition. We could have directly derived the strong Wolfe condition, but in many papers or literature you will find people just doing Wolfe condition. So then you should not think that they are doing strong Wolfe, which is why I have mentioned this over here. Alright, then practical issues of finite differences in calculating gradients, and your first algorithm for line search, which is backtracking, right? So fairly easy stuff. Remember, we are not going anything beyond first and second order Taylor's theorem. So if you can keep that in your head, everything is a piece of cake. Okay, any questions? Yes. Yeah. Correct.
So then once we reach the first peak,
Yeah.
beyond that point, the magnitude of our slope increases.
Correct.
But then that falls under the alpha that we choose.
Yes, in the strong Wolfe condition.
Yes, sir. So how are we able to take a scenario where the magnitude of our slope is increasing? Because it shouldn't it be until we reach the minimum, and once before reaching the maximum, at some point the magnitude of the slope increases. The portion from
Okay, so this is the trouble with drawing a graph is that drawing a graph is very cheap. I can draw the graph perfectly. When you look at it, you can say, hey, what's the point in doing anything after the minima? On a graph, it's very easy for me to see. But now look at your backtracking line search algorithm, right? So that means I'm starting at some value over here. All I'm going to do at this point is to evaluate the function. So I get one dot of this function. I don't know where the minima is, whether it's to my left, to my right, right? Then I multiply it by rho if it is not good enough. I'll make a discrete step back. I'm not tracing the curve of the graph. So this curve of the graph is only to enhance the understanding. Actually, I don't know how the graph looks. So when I put these strong Wolfe conditions on this graph, you can see that it is restricted. That you will agree that those within alpha within that range satisfies a strong curvature condition.
So that's it. The alpha is chosen from the minima to like you're choosing the alpha to be from the left of the minima to
To the right of the minima.
yes. So the portion from the minima to the right of it, how does that satisfy strong curvature? That's what I'm not.
Oh, well, because I put a mod sign over there, right? So the slope on the left point is less than C2 times the slope at the origin. That you agree?
Okay, as long as it's less than that particular.
Correct. The check is always with the slope at the origin, C2 times that. So on one side it's plus, on the other side it's minus. So I'm bracketed inside it, right? So keep in mind, this drawing a graph is a luxury which we are using for understanding. In practical life, we will not be able to draw any graphs. That's why we need rules which could be evaluated on a function value. Yes, no. That's what an algorithm does, right? There's no, you never tell a algorithm draw the graph, right? I can't do that in 1 million variables. Yes, question. That's heuristic. Yeah, that's heuristic. Why C2 less than C1 is all of the choice of C2 and C1 is heuristic. I vaguely recall an exercise where we tried to work out that C2 is less than C1. If I find it, I'll put it in the tutorial. Okay. Are there any quantitative algorithms to quantitative analysis to tell which algorithm is faster? So in the subsequent modules, we will look at calculating the convergence rate for different algorithms, for gradient descent, for conjugate gradient, and so on, right? So that will give us an idea of which method will be faster or not. But you are saying that, for example, for different stopping conditions, which will be faster? I mean, in the optimization literature, all of this has been analyzed. But broadly, supposing, for example, I fix it to be gradient descent, the rate of convergence is linear. Now, when I say rate of convergence is linear, the coefficients, it's order notation, it's linear, but the coefficients can change depending on the implementation. If I'm checking this condition versus that condition, order remains linear, but the constants of that order will change. So some may, be faster, some may be slow. That is bound to happen. Okay. And then we sort of stay away from that territory, because then more and more it becomes implementation dependent. Did you have 100 cores or did you have 1 core? How well did you do parallelization? All of that matters, right? Because if I have a 100 core CPU, the sufficient decrease condition and the curvature condition may be just as, if I can do n simulations in parallel, I can get the gradient in the same time that it takes me to get a function value. Then they run as fast. But if I had one CPU, it changes, right? So, we'll keep it at a little higher level, because then we'll get lost in implementation detail.